One of the key drivers in advancing technology since the Industrial Revolution has been new ways to store energy, from coal and oil, which store chemical energy that's released when they burn, to batteries, which store electrochemical energy and can be used to generate an electric current. When we look around the modern world, we see batteries everywhere, from phones to laptops, and now even electric vehicles. But they're very limited, and need to be improved if we want to see a future with zero-emission transport, smart energy grids, and phones which can charge in under a minute. Much of the portable technology we use today is powered by lithium-ion batteries, and these wouldn't be possible without graphite, like you find in a pencil. The atoms of graphite are arranged in flat layers, like the pages of a book. This allows lithium ions to easily move in and out of graphite, and so when hooked up to a lithium-ion battery, lithium ions can shuttle back and forth between opposite electrodes, an anode, which is made of graphite, and a cathode, which is made of another layered material, such as cobalt oxide. Because the lithium ions are positively charged, electrons have to keep up with them as they go back and forth between the electrodes, but they have to go around the long way, through a circuit, which is what powers your phone. So where does graphene come in? Well, lithium-ion batteries have been around for a long time now, and scientists are now developing batteries that will make phones last for longer than a day, or charge up in just a minute. Using graphene instead of graphite means that there's more space in between layers, and so lithium can move more freely, and batteries can charge up in a fraction of the time that they used to be able to. Alternatively, it also means that larger ions, such as sodium, can be used to replace lithium. This is great because lithium is actually very rare, and larger elements like sodium and aluminium are some of the most abundant metals on Earth, making batteries much more sustainable. So that could make your phone charge faster, but how about making it last longer than a day? Well, besides graphite, there are a number of materials, such as silicon and sulfur, that can store way more energy, but they aren't able to be used in rechargeable batteries because they take too long to charge, and they lose their capacity too quickly. If you complain that your phone takes an hour to charge now, and it doesn't last as long as it used to after a year of owning it, imagine if it took all day to charge, and after 2 weeks of owning it, your phone died within minutes. With silicon, the capacity drops so quickly because every time the battery is charged and discharged, silicon particles can expand and shrink by over 400%, causing the electrode to fall apart. With sulfur, the capacity drops so quickly because when lithium leaves the electrode, atoms of sulfur like to tag along for the ride, and those lithium ions remain bonded to that sulfur forever and can't be reused. People are using graphene and other 2D materials to solve these problems by using them like a scaffold that can hold silicon or sulfur particles in place. Within this scaffold, silicon particles are free to expand and contract as they please, and the scaffold can also act like a net, meaning lithium ions are unable to move to the other electrode until they have broken their lithium-sulfur bonds. So how do batteries fare against other energy storage systems? Well, the gold standard for a long time has been oil, just a single litre of which stores enough energy to drive a car for 10 miles, and in a jet engine can release that energy quickly enough to accelerate a 747 into the sky. Compared to oil, today's batteries aren't too bad when it comes to capacity, the amount of energy they store, but they simply don't have enough power to ever lift their own weight off the ground. Slightly different to batteries are supercapacitors, which work in a similar way, but the ions don't have to travel as far, and they don't form true chemical bonds with the electrodes. This means that they can't store quite as much energy as batteries do, but they release the energy which they do have in a fraction of the time, and this is ideal for applications that require short bursts of high power. For instance, supercapacitors are used to blast open the emergency exit doors of aeroplanes. Finally, we have fuel cells, which are similar to batteries but can store even more energy, meaning that in an electric car, for instance, you could travel a much longer distance before needing to fill up.
Now that we've seen how batteries work and store energy, we need a clean and efficient way of creating electrical energy to fill these batteries up. This is water, and water contains hydrogen. Hydrogen is the most abundant element in the universe, and it powers all life on Earth as we know it. So why don't we use it? This graphic shows how a hydrogen economy could work. Firstly, hydrogen needs to be produced. It can be made by harvesting electrical energy from wind, solar, or other clean sources. This electricity can then be used to split water into oxygen and hydrogen. This hydrogen can then be stored in a number of different areas. For example, it could be used in hydrogen fuel cells that power cars or for other personal energy uses. It can be used in large-scale industrial processes to make fertilizer or other chemicals and materials. But the great thing about hydrogen fuel cells is that the waste products are only heat and water, so it's a very clean energy source. If we compare it to other energy sources, hydrogen fuel cells are very efficient, having an efficiency of around 60 to 80%. They can also give a range of power outputs from low personal use of 30 watts to larger outputs of 3 megawatts. Coal and nuclear power stations are around 35% efficient and cannot be increased much higher due to thermodynamic limits. However, they do produce a lot more energy of around 2 gigawatts. But the energy they produce comes with lots of dangerous waste. Their setup and decommissioning costs are very high, and so are their environmental costs. Whereas fuel cells are clean, efficient, they're silent, they don't require lots of space to run, they will run continuously as long as fuel is supplied, and they don't pollute the environment. They can also be scaled for different sizes, for different uses. So how do they work? Fuel cells are very simple in design and easy to set up, and it was first demonstrated in 1839. So this is an old technology. It utilises hydrogen and oxygen to generate electricity. Hydrogen is pumped into the negative electrode. Here it reacts with a catalyst to produce protons and electrons. At the other side of the fuel cell, oxygen is pumped in at the positive anode. Then by connecting the anode and cathode together through an external circuit, electrons can then flow, producing electricity, which can be stored in batteries or be used to power things. But the most crucial part of the fuel cell is the electrolyte. This should be a semi-impermeable membrane that only allows protons to pass through it. The better the electrolyte is at allowing protons through, the better the fuel cell. So most fuel cells use a polymer electrolyte as it's easier to handle and less dangerous. There are a few problems with fuel cells though that reduce the efficiency and power output. And the two main problems are fuel crossover and resistance. And these two are linked together, which introduces an annoying trade-off. Fuel crossover is when oxygen or other unwanted molecules pass through the electrolyte in the wrong direction. In reality, electrolytes are not perfect and some crossover will occur, and this reduces the power output. One way to reduce this fuel crossover is to use more electrolyte, thus increasing the distance between the anode and cathode. However, this reduces the flow of the protons through the electrolyte as it increases the resistance, and this reduces the current flowing through the fuel cell. But if we reduce the thickness of the electrolyte, we then run into the fuel crossover issue. This is where graphene and 2D materials can help a lot. Monolayer graphene blocks all gases, molecules, ions and atoms except for protons. And this is due to the carbon ring structure of graphene. And this means that graphene can be used in fuel cells because the graphene will stop all gases and ions from passing through it, thus reducing the fuel crossover issue, which also means that we can reduce the thickness of the electrolyte, meaning that the current can be higher. Therefore, we can increase the efficiency and power output of the fuel cell. It's also possible to use other 2D materials, such as hexagonal boron nitride, which has the same structure as graphene, but contains boron and nitrogen atoms instead of the carbon atoms. It has been shown that hexagonal boron nitride is better at allowing protons through, although it's harder to make than graphene. Fuel cells also have other benefits. Potentially the most applicable place for fuel cells is in space exploration. The potential power hydrogen reactions have is huge, and a form of rocket fuel is just the reaction of oxygen and hydrogen. If we can place fuel cells on board these rockets, then the crew inside will have power for long journeys, but they can also create their own water. Once we've gotten to this new planet, we cannot fall into the same mistakes we have on Earth and pollute the place. Therefore, we could use hydrogen fuel cells. The hydrogen found there could be used to create our own water for drinking and farming, and it could also produce the electricity needed to power the space station and life on another planet. Hydrogen fuel cells really are a viable option for us to produce electricity here on Earth and hopefully on another planet. They're simple, require no moving parts, and are clean and efficient. and with the help of graphene they can be made even better. 2D materials are making huge advances in battery technology and energy creation, helping us to produce a greener, cleaner, more efficient economy for our future.